Ah, victory.
I guess so.
Okay, so let's go. So this is joint work with 3 other folks at Microsoft: Colin Reed, who works in a product group, and Mingwu, who is a researcher in MSR in Beijing, and Xinhao Yuan, who's an intern of his in Beijing. So what I'm going to describe is a new algorithm for concurrency control on tree-structured indices, which is basically any database system you currently look at, unless it's purely hashing and has no tree indexes in sight. It's called Meld, and let me just start with some motivation just to give you a feel for where it fits in the system. We could talk the whole time about the system. Happy to entertain questions about this, but the main body of the talk is the algorithm itself. One is a data sharing system where the log is the database. All right. There's not a log and a database. The log is the database, and all servers can access it, so it's a data sharing system. Each transaction appends its after images to the log as a single record. So it runs locally against its local copy of the data, cached copy, generates its updates, appends them to the log. No concurrency control at this point, except for whatever arbitration is needed to make sure the log is sequential, because they all have to add it in sequence. You don't want their log records interleaved. And then the log is then available to all the servers, and they all roll forward the log in parallel, independently, and use optimistic concurrency control to figure out which transactions committed and aborted.
So, quick question. So every server has a different view of where the log ends?
Well, they're running at somewhat different speeds, so they're not going to be perfectly synchronized. So, so the question is whether they have a different view of where the log ends. And yeah, due to timing variation, they will. But there's only one copy of the log. There's no possible disagreement as to what the sequence of records are in the log. They just might not all be up to the last record. Yeah.
So also, I just want to make sure I understand the background. So we start, let's say I load data in my database, and that will be maybe the prefix of the log.
Right. Think of it as a big bulk transaction that populates the database.
That's right. And then when the servers start, each server is going to on demand grab pieces of that.
Right. All they need, the database is a tree. All they need is a copy of the root, just like of any database. You get from the database root, you can get to all of the sub-databases, and from there you can get into all of the sub-schemas, and from there you can get into all the tables, and then all the rows of the table. No, just in the standard way. So they would start up just by getting the root, getting a handle to the root, and then they can just run transactions in the usual way. And they'll just grab data on demand off of this log.
I see. So they all know kind of how far into the log they got, and then they're going to kind of roll the log forward if they're behind.
They all know how far.
I mean, so like if I'm a server, right?
Yes.
So let's say nothing happened yet. We just have this bulk load transaction, and then someone wants to do an update. So server A will say, well, I need to get from the root, maybe I need to go down.
So each server has a copy of the root. Each server independently, when it runs a transaction, searches for the data that the transaction needs. It says, get me record so-and-so, and it just goes and starts accessing shared storage, which happens to be the log, to trace through the path to get the record that's being requested, and it pulls that stuff along the path back up into the server cache, just like it would in any database system. It just so happens that the data is sitting in a log. It's not in the database. The database is the log. That's all there is.
So the log has an API that kind of hides that.
And yeah, the log is basically a page-oriented storage that is network addressable. So the server, when it gets just like today, if your database system accesses a page, it knows to go through the volume manager, blah blah blah, and eventually knows what address on the disk to pull in. Same story, exactly the same story here. So there's a whole story. This is a simple block diagram, obviously very complex system, lots of layers. But the logic, the reason why we did this, we actually built this, is that if you're working with flash storage, the storage is log structured. It's inescapable because in order to balance the erasing of data on flash memory, you basically have to use log structured storage. So why not just make that the database and just have the log be the database, so then you don't have to go through this translation where you have this random access to the data and then the updates go to the log and the log goes to SSD, which is simulating a random access device on top of physical memory, which actually wants to be log structured anyway. I mean, it's just the whole thing. There's just all this complexity, and it's all there because we're used to using disk drives, which behave very differently. Well, until recently, actually disk drives are becoming tape also. It's actually, we're getting to the point now, the next generation of disk drives will not physically be randomly updatable because the tracks are getting so close together that they can't reliably write sectors of the track in the middle of the disk. They have to do appends because, you know, it's called shingling, where the tracks actually overlap a little bit. So all these mass storage devices are becoming log structured. So, you know, it's a research project. You know, you try it out and just see how far you can push it. But this is one area. So the optimistic concurrency control is that each server, when it appends its updates for this transaction to the log, it knows what state of the database the transaction read, some earlier point in the log. It knows where this log record landed. And because it sees the whole log, it also knows all about all the updates in between. And so now the question is, did this transaction experience a conflict? You know, between the time it was reading this state here and the time it recorded its updates here, was there some update along the way of a committed transaction that conflicted with this transaction's reads or writes, depending on the isolation level? Writes if you're snapshot isolation, reads and writes if you're serializable. Right? And all the information's in the log. So you should be able to figure it out. That's optimistic concurrency control. That's the algorithm we're going to look at. So let's look at another scenario. Here is a multi-core system. So this is one computer now that has multiple cores, and let's suppose that the cache memory is actually shared across the cores, as it probably would be. And then storage is again the log. The database is again the log, and that log could be in main memory or in physical storage or in non-volatile storage. The same issues will apply here. Because the cores are running independently, that could potentially actually be a log-structured shared memory, if you will. So same scenario, and now you have one core which is dedicated to rolling forward the log against the cache. So one of the things about multi-core is that you do not want to experience context switches between cores, because it's very expensive. You know, you basically really want to. There's so much processor context that would get lost that you really don't want to do locks. You don't want to do delays and coming, you know, IOs and then coming back. You really just want to run from beginning to end. And so here, that's the scenario, is that the transaction's running against a snapshot of the database. It runs the transaction till the end. It appends the updates to the log. And then this other core, which is running this optimistic concurrency control algorithm, is processing the log and figuring out which updates committed and aborted and recording that information in cache asynchronously so that these cores don't interfere with each other. All right, so that's another scenario that this might be useful. So in the absence of questions, that's all the motivation you're getting. So, yeah.
When does a transaction commit? When it has established that there was no conflict?
When does a transaction commit? The answer is that after the roll forward has processed that record, that transaction record, and determined that the transaction has committed. So in particular, the server that ran the transaction and that appended the updates to the log doesn't know whether the transaction committed until after its own algorithm that's doing the roll forward has gotten that far, because other servers will also be appending to the log, and this server has no way of knowing about that until it's actually appended its transactions record and has seen everything that came earlier. And I'll emphasize, the issue is whether there are any conflicting updates to any conflicting updates by committed transactions between the point where the transaction read and, because there's a lot of transactions being appended. They don't all commit. It's only the committed ones that are going to cause this transaction to abort. Okay? Yeah.
So do transactions write to the log as they're in progress?
No. Transactions do not write to the log in progress. They write locally, and when they're all done, they package up their updates, the after images of their updates, and they package them up into a data structure that goes into the end of the log. And I'll give you some, I'll explain that a little bit in just a moment.
So, but the only stuff in the log is committed stuff, or stuff that the individual processes think they're committed?
No. So the question is whether the stuff in the log is committed. The answer is no, not necessarily. What goes in the log is the result of having executed a complete transaction. Whether or not that transaction committed will only be known after the roll forward has gotten through that record and seen whether there were any conflicts.
Maybe another way to ask that same question is, if a processor is executing transactions locally, it can probably kill some of them, abort some of them, because it knows if they will not commit, because of other local transactions.
Yes, yes. So the question is whether it's possible to abort a transaction sooner than appending the transaction to the log. And the answer is yes, because it could be that this roll forward locally on your server discovers a committed transaction that's already in this range that's going to affect this transaction. And so there's no point in continuing because you know that it's going to die anyway. Okay? All right, so let's take it down a level of detail to look at the execution model a little better. So I'm assuming the database is a tree. For purposes of the talk and the paper, it's a binary search tree. It could be a B tree. We've done it with B trees. It's not significantly different. So the tree, therefore, when you write a set of updates, like a tree to the log, you have to marshal it in sequentially. This is how we do it. So it goes leaf to root, left to right. Now, the database is multi-versioned, which means copy on write. So you never update a record or a node in place. If you want to update a node, then you create a copy of the node. So if a transaction updates node D, it creates a copy D prime. Now, D prime is sitting there, and it's not reachable from the database. So you have to create a path to it. So that means you have to create a new copy of C. You can't update the old copy because you can't update in place. So you've got to create a new copy of C pointing to the new copy of D. And you kind of get the idea. So then you have to create a new copy of B and then a new copy of G. Notice that the paths, you only have to update the pointers on the path up to the root. The other subtrees are unaffected, but there will be pointers to it. So B prime, which is a copy of B, has a new subtree down the C side, but it's the old subtree down the left side, the A side. Yeah.
This means that every transaction rewrites the root?
Yes, so every transaction writes all the way back up to the root. Yeah, Abhay?
So isn't all the data at the leaf? You have data in the interior nodes as well?
So the question is whether there's all the data is at the leaf or the interior nodes. In this presentation, I'm assuming there's data in the interior nodes. Again, we've done it both ways. There's an argument for having it be at the leaves.
Yeah, if it's only at the leaf, then you won't have to go to the root every time, right?
You do, because you still have to update all the way up, because if it's at the leaf, you still have to create a new version of the leaf, which means that you can't have. See, what's going to happen is while a transaction is running, it's got a stable version of the database. So when the transaction starts, it gets a copy of the root. All right? And while it's running, other transactions are committing, and they're create. So you don't want to disturb this snapshot that this transaction is reading. So you can't let somebody update leaves in place because they all need to have paths to
I
it.
was thinking of like a B tree, and the data is only at the leaves.
Yeah.
So suppose there is an interior node, and it says it has all the data between this range, and you update the leaf and you update its root, and the root does not change; it still remains the same. So you don't
No, it does. So the scenario you just described is you modify a leaf. that causes its parent to have a new pointer to the leaf, but its parent cannot be updated in place. Nothing in this system can be updated in place, because then you would be altering the snapshot of some transaction that's already running, and they can't do that. This is, by the way, this is standard multi-version stuff. This is just how these systems work. You may not have thought about it before, but it's, this has been around for a long time.
I should mention
Yeah.
it was standard in Lisp.
Standard in Lisp? Yeah, well, any functional language has the exact. In fact, I have a funny story about that at the very end. You might. I think I have a slide on it. We'll talk about that.
That should be scenario 3, right? A Haskell system.
Yeah. I'm slowly getting to know those people, because we're finding that.
Persistent Haskell system. That's a killer app for you.
Right. So we're going to use the first scenario just to drive this so you understand how the execution goes. So every server has a cache of the last committed state that it knows about. When a transaction starts, it gets a pointer to the snapshot, to the root of the latest state. It runs locally. It generates updates. And when it's all done executing, it takes those updates, it appends it to the end of the log, and that update record includes a pointer back to the state that the transaction read, so that when we do the roll forward, we'll be able to figure out which transactions in between are the ones that are relevant for the commit or abort of this transaction. This is all conceptual. It's not actually like this, as you'll see, but this is the concept. So the question then is, did a committed transaction write into this transaction's read or write set somewhere in this range between the state that it read and the point where it did its updates? So each server process is going to, or each server will process these records. We call these intention records because they're what the transaction intended to do. Whether they did it or not, we'll find out. And it will check whether the transaction experienced a conflict. If not, then the transaction committed, and so the server will merge the transaction's updates into its local cached copy of the state. All servers are looking at the same sequence of log records. They're all making the same decisions. Therefore, all servers are learning about commit and abort of the transactions independently. Now, standing back from this, the maybe amazing thing is that these servers aren't talking to each other, right? The only point of arbitration is appending to the end of the log, right? There's no lock manager, there's no crosstalk between the servers, there's no partitioning of the data. It's a complete free-for-all, and yet they all are able to run transactions at any isolation level you want. Now, so where's the catch, right? Well, there are a problem. There's performance limitations here. We'll get to that in a second.
So when the transaction discovered that it can commit, don't you need to write another log entry to announce to the world that this transaction?
So the question is whether when a transaction is known to commit, you have to write another log entry to indicate that fact. The answer is no. We don't actually do that. You could, but we don't. We do allow checkpoints to happen periodically, because what if a server? There is a problem when a server comes up and it's got this big log out there. How does it know where to start? Because it doesn't know which transactions have committed. What it's supposed to do? Start from the very beginning, and do the whole roll forward from the beginning of time. So there has to be some notion of checkpointing here, so there's a place to start. And that notion of checkpointing is going to have to indicate something about which transactions committed or aborted, or some way of getting at the last committed state as of some point in the log.
Even without checkpointing, are you going to show us how a server who reads a log can distinguish between the intention records that have eventually committed and those that have?
So the question is whether a server can distinguish between the intention records that have committed and not. No. Each server will have a cached copy of at least the top portion of the last committed state it knows about. That's all it needs in order to be able to run transactions. And so it's only going to, once it starts, it's going to start searching. Whenever it runs a transaction, it's going to grab the root of the last committed state it knows about, and it's going to run against that state. And that tree is going to, in turn, if you go deep enough, is going to start accessing data out here in the log that is part of the intention records of transactions that contributed to that last committed state. But per se, the server doesn't know. I mean, if you just sort of pointed it at a transaction and said, did that one commit, it doesn't know.
So I guess, if I've got this right, then the deal is that all the servers are running the algorithm and making the same decision because everything's right.
All the servers, yes, all the servers are processing the same log using the same algorithm. The algorithm is deterministic down to its finest detail.
So there's no need for a commit record or something.
So there's no, right, so they're all going to make exactly the same commit and abort decisions. Notice in particular that the server that ran the transaction, in answer to Dan's earlier question, the server that actually ran a given transaction, it doesn't know whether the transaction committed or aborted until it rolls forward. The only difference is that it will actually return the decision back to the client that issued the request. The others won't do that. Yeah, Magda?
And are you going to rely on the fact that the memory that holds the log is extremely fast and the network is extremely fast to avoid aborting like crazy?
So the question is whether the performance characteristics are such that optimistic concurrency control won't cause too many transactions to abort. And yeah, I mean, there's engineering to be done for that. You know, that's why we got to write some nice papers, is to show how that is possible. So let's get into the performance. Let me just, I think I'm repeating this over and over because the algorithm won't make much sense if you don't see the system. So the transaction flow is you run each server has a local copy of the last committed state, runs a transaction, generates an intention. Intention gets appended to the log. Presumably the log is being broadcast back to all the servers. One way to do that is to have each server, when it appends the record to the log, to also broadcast it at the same time to all the servers, and then for the servers to periodically get a batched acknowledgement from the end of the log that lists the sequence of log records based on some unique ID in the log header. So that somehow you've got to get it so that they all know exactly what the tail of the log looks like. If messages get lost, there's no problem because the site will be able to detect that there's a hole, and it can always go back to the log to read what was in the hole to see which record landed in that slot. So lost messages are not a problem. And then the log is rolled forward. That algorithm is called Meld. That's the subject of this talk. I haven't gotten there yet, but any moment now. And it's making the commit and abort decisions. The aborted transactions go in the garbage. The committed ones have their updates merged into the last committed state. So performance. What's going to make this thing fail? What's going to slow it down? Well, for one thing is we've got to broadcast the intention record across the network. Data center networks are currently mostly gigabit Ethernet. We're going to 10 gig. Transition's happening right around now. It's not quite commodity, but people are starting to deploy it. 40 gigabit, 100 gigabit standards are already done. So people are already prototyping hardware. There's initial hardware available. It's going to be some years before this stuff is cheap enough and widely available, but it's all coming. The network's going to get faster. Appending to the log, well, that's a combination of storage and whatever electronics you use in order to process the append operation to storage. That's going to get faster. Optimistic concurrency control, well, that depends on everything else, right? It's sort of the faster, the less time there is between the transaction reading the last state and appending its updates to the log, the shorter that space is in the log, the less chance there is that there's going to be an abort. And also it depends on transaction workload. Just, do transactions conflict a lot? Are they reading and writing the same data? So there's not much we can do about that other than to speed up everything else. And then finally, there's meld, which is this single-threaded process that's going to roll forward the log. We can parallelize it to some extent. We're going to work very hard to parallelize it. But in the end, it must make its decisions based on the exact sequence of the records in the log. There's nothing you can do about that. And the one thing we know is that single processor performance is the one piece of the system that's not going to get faster, or at least not by very much. So it's very important in the scheme of things to get that meld algorithm to be as fast as we can make it. That's why we focused on it. You know, we did the other stuff too, but this was the one where we felt we really needed to find out what the limits are to performance. So we optimized the heck out of it, and we built it, implemented it in C++, measured it, actually implemented it several times, and in order to understand just what are the limits to performance that are possible here. And that's what we're going to talk about, finally. Okay. So, the main idea, there's a couple of main ideas, but the main idea, if there is one, is to quickly find conflicts as high in the tree as possible so that you can bail out either because you know it committed or you know it aborted without having to actually look at everything in this intention record. So, for example, suppose here, this is the transaction's intention. It only wrote part of the tree. That's why it looks funny. And in particular, somewhere embedded in here, there's a little subtree called X, which has a root. And that value of X, you know, it had some state back when the transaction started, and then it had some state in main memory, which was the last committed state as of the moment we're going to meld this record. And then there's the state of that subtree in this record. You got that? So we got a little subtree, right? It had some state when the transaction started, and then by the time we meld the transaction, it has potentially a different state because lots of other transactions may have committed in the meanwhile. Right? But suppose that we find that the version of X, which the transaction read back here, is identical to the version of X that it sees in the last committed state. So it's looking in, you know, we're doing the meld, it's looking in main memory, and it says, gee, you know, this tree that I did all kinds of mutations on this tree. But the state of this tree now, right after all the committed transactions have run, is identical to the state that I read. So nobody touched this tree. So therefore, I'm free to do whatever I want to it. There's no reason to dig into this tree any further. Just replace the entire subtree by what I wrote.
And by identical, you mean it has the same pointer, the same.
I've got to have enough metadata about that tree to know that nothing changed. Now, remember that, well, let me just leave it at that. You'll see. It's pointers change, and they don't always change because some content has changed, as we saw earlier. They might just change because, you know, this subtree over here happened to have some ancestor was on a route to something else that changed. So actually, you can get misled as to what actually has changed just by looking at pointers. Okay. So, all right, so let's look at the algorithm. So there it is, high-level algorithm. Takes the last version of the database state as of the last committed transaction, the intention record, which is the very next record in the log, and it produces a new version of the database state, which is either identical to the old version if the transaction aborted, or it includes the updates of the intention record if the transaction committed. It's got to be fast. It's got to be deterministic because we're going to run it on every server. All right, so this is the example I'm going to use. We start out running a transaction that writes this tree. Has 4 key values, B, C, D, and E. It then runs 2 transactions concurrently, one of which inserts A. Now, since it inserts A, it has to modify B and D, as I described earlier. And then transaction 3 is inserting F, and it therefore is going to modify D and E because. Right, so A and F, they're completely independent. These transactions clearly do not conflict. So what we want is we want them both to commit. We want all these transactions to commit, and we want the result to reflect their combined effect, which is the update, the insertion of A and the insertion of F, which means we're going to need other values for at least for D, we're going to need another D that's going to point to that B and that E. All right? So that's going to be the test case to see. That's going to illustrate most of what's going on in the algorithm. All right, now we're finally getting into the details. So each node in the tree has metadata. It has information about the version of the subtree and dependency information. This node metadata, some of it's in the intention record, some of it's in the log, which is the database. But in the end, they're both the same thing because everything that's in the database is in some intention record and hence was in some, as part of some transaction's output. So all this metadata gets written by each transaction as part of generating its intention. So every node has a unique version number which permanently identifies the exact content of that node subtree. If anything in that subtree changes, then the version of that node is going to change because it's going to propagate back up to that node in the root, and you're going to have to create a new copy, and that's going to create a new version. That doesn't mean that the data in that node changed. It just means something in the subtree changed. So every node in an intention stores metadata about not only the state that it wrote, but also the snapshot that it read. Because in order to figure out whether there's a conflict, it's going to have to compare information about the snapshot that it read against the state that's in the last committed state now in main memory. And it doesn't want to have to go searching through the database to figure that out since we want to run this algorithm really fast. So, all right, so we're going to keep track of the version of the transaction snapshot and other dependency information. So it's the transaction depends on the previous state of that node, and what's the nature of that dependency? Is it because it read that data, it overwrote that data, it read something in the subtree, we're worried about phantoms, there's something about a key range that it knows was unaltered. There's a variety of dependency information you might want to keep depending on the degree of isolation you're trying to enforce. Each node's metadata compresses down to about 30 bytes. So it's not insignificant, but it's not a gigantic amount either. Right?
Is that complete in some sense, like for all the isolation levels?
Yeah, we can handle all isolation levels, yeah, phantoms, the works. Yeah, this is, that was part of our goal in building this was, when you build it, this is a brand new concurrency control algorithm. I mean, optimistic isn't. By the way, you look in the literature, you can't find anything really on the details of how to implement optimistic concurrency control efficiently. I mean, you can find books on how to do locking, lock managers and sample code and, right down to the goriest details. But for optimistic concurrency control, there's this high level, well, you're going to keep track of the read set and the write set, and you're going to check for conflicts, and that's about all they say. So as far as I know, this is really the first very detailed description of how to do it, obviously in an unusual scenario, so it's by no means the only way to do optimistic, but it does bring you down to a level of detail that is worthwhile writing about. I mean, I wish people would do this for other data structures and system scenarios. All right, so how do we do these version numbers?
You said each node's metadata compresses to that much. Shouldn't the size depend on the height of the node?
Does the size of the metadata determined in part by the size of the tree? No. You'll see. All right. So how do we assign version numbers? Now, this is one of those nasty, if you don't sit down to build something, you sometimes forget that some of these things can be a challenge. You're running transactions independently on different machines. You don't know where they're going to land in the log or in what order. How do you assign version numbers so that they monotonically increase? And you don't want these servers talking to each other or to a lock manager or anything else. So how do you do it? So here's how we did it. So we're going to store the nodes in an intention record, and they're identified by their offset within the intention record. So relative to the intention record, we know what their version numbers are. And after the record has been written to the log, we know what its base version number is. It's one more than whatever the version number was of the one that preceded it. So the meld algorithm will actually figure out what the version numbers are. In other words, the server that's generating the transaction record at the time it does the append, until it actually sees a response, does not know what the version numbers are of those nodes. It's just set it up so that meld will be able to figure out what they are at runtime. They're not stored anywhere. At least I should say, they're not stored within, the version number of a node is not stored with the node. There are many other nodes that store those version numbers because they're trying to keep dependency information, but the node itself does not store the version number. But at the time some node cares about the version number of some earlier node, that earlier node has already been written to the log and therefore can be known to the transaction that wants to store the dependency on the earlier node. All right. So here we've written B, C, D, and E in the order you see here. Let's suppose that the previous transaction had an absolute version number of 50. That means C is version number 51, B is 52, and so forth. They're just +1, +2, +3, +4. Okay? Now, the metadata, I said each node has metadata. The metadata of a node includes the version number of that node in the transaction snapshot that it read. So I've got a node that the transaction is working on. It's going to end up storing it for some reason because something in its subtree changed. It's going to store it in its intention. And it's going to include the version number of that node in the snapshot that this transaction read. Okay? That's called the source structure version. The names, there's a proliferation of names here that are unfamiliar because we're inventing various kinds of metadata that has to be stored that we don't think there's going to be a bunch of these terms. Try to keep it straight. The node will also have a bit called depends on, which indicates whether the transaction depends on that node not having changed while it ran. Now, just because it's keeping track of that version, that doesn't mean that it depends on that node not having changed. It might be able to benefit from that knowing that that node hasn't changed because that would tell it doesn't have to drill any deeper in the tree. But it might not depend on that node having changed because it could be the only reason why that node changed is because something on subtree that's unimportant to this transaction changed. And that if you drill down deeper, when you finally get to a node that it actually depends on, then it will turn out that that subtree did not change. So it was, something higher up changed, but only because something this transaction didn't care about changed. All right, you'll see an example of this. And this gets back to the original motivation of trying to truncate the search as early in this meld process as possible. So let's, in this case, this transaction inserted these nodes for the first time. So the source structure version for all of them is 0. But let's say it depends, having inserted this, it depends on the fact that the tree was empty initially. So the source structure version for D is 50, refers back. It depends on the fact that this node And it actually has the dependency bit on it. Depends on the fact that the tree was empty, otherwise it wouldn't have inserted all these nodes.
So Bill, just for expository purposes, is there like a minimal amount of metadata you need to just do this at all, and then the rest of these pieces of metadata are all sort of optimizations of various types to do this truncating, or should I
I'm not sure you need any of the metadata. I have to think about it, because if you know all of the updates,
just run it?
you know, you might have to diff node content to figure out whether something changed. You might have to drill, but it'd be a lot of running around in the log to figure it all out. All right. All right. So this says that the root of the subtree depends on the previous state. Now, during meld, when this transaction comes along, the meld process will look at the root. Remember, okay, so the way the meld process works, for each transaction, it's going to traverse the intention top-down. It starts at the root, traverses top-down. So it starts at the root, sees D, sees that D depends on version number, the node version number 50, and it sees that that node 50 is actually still present in the last committed state, unchanged. Therefore, nothing happened in between the state that this transaction read and the time when it wrote its updates. So this transaction is committed immediately after meld has looked at the root. Doesn't have to look at anything else. All right, constant time, looks at one node. Yep.
But I'm still stuck to what you answered to Bill. So you said that if you didn't have this metadata, you could reconstruct it.
I think so.
But you also said that the reason why the SSD for D is 50 is because transaction T1 had to check that D was at the
Oh, you're right. I need to record reads. I need to distinguish reads from writes in the intention record.
So you need to know it.
Good point. Yeah, which I haven't. And that information. So you're correcting for the internet audience. My answer to the earlier question was could meld function without any of the metadata? I said yes. That's not quite right, because the intention record, as it stands, doesn't distinguish which nodes were read from which nodes were written. You need to know what was read in order to determine read-write conflicts if you want to run at serializable isolation levels. At weaker isolation levels, that wouldn't be important, but you're right. Okay. So that was an example of a serial intention. A serial intention is one whose source version is the last committed state. And in fact, T1 was a serial one, and T2 is as well. Remember, T2 and T3 ran in parallel off of the result of T1. And let's say T2 got logged first. Doesn't really matter, but let's say it did. Then T2 depended on the state that resulted from writing T1. And that state was in main memory at the time that T2 ran. So that means that T1 must have been melded and in the last committed state in memory. Otherwise, T2 could not have read it. And so it knows that the version number of the root that it read was 54. Right? Because it had that in main memory. And meld, when it processes transaction 2, again determines that the state of the root in the last committed state is identical to the source structure version of the root in the new transaction. Therefore, nothing happened in between. Therefore, the transaction committed. Again, without drilling deeper into the record. All right, so we've run transaction 1, we've run transaction 2, now transaction 3. Transaction 3 also ran against the result of transaction 1, so the source structure version of the root of transaction 3 is also 54, which is the result of transaction 1. But meld, when it compares them, says, oh my, they're not equal. The tree has changed in between the time transaction 3 read it and the time that it does the meld. So what does it do? Well, it it doesn't depend on that state. I mean, all it's depending on is that it wrote a new F. So there's no dependency. This doesn't cause an abort because it recognizes the only reason why apparently the root changed was because something deeper in the tree changed. We happen to know that that something deeper is A and has nothing to do with this update, but Meld doesn't know that yet. And so what it's going to do is traverse deeper. Remember, Meld is driven off the state of the intention, so it just goes top down through the intention. So it goes down one level and it looks at E. And it looks at E and it compares E to the value of E in the last committed state. Now, how does it know that that's where E is? Well, you have to think about how this traversal is going. So I've got the algorithm has sort of, if you will, it's got one hand on D over here, and it's got one hand on D in the last committed state. And now it goes down a level in here, and it goes to E. So it's going from D to E, so it's going down the right branch. And so, okay, well, it's got to go down the right branch of D in the last committed state to see if it can find E. And so when it goes down that branch, it's going back to the value of E actually in transaction record 1. It has no idea that it's in transaction record 1. It doesn't care. I mean, actually, if it analyzed the pointers, it could figure out that it actually is in an earlier intention record, but it doesn't really matter. So it just grabs E, and it looks at the version number of E and compares it to the source structure version of E in this intention record. And again, it determines they're the same. That means that the subtree of E in the last committed state is identical to the subtree that was read by transaction 3 at the time it ran. Therefore, it doesn't have to drill any deeper. There's no conflict. Transaction 3 is committed. And in particular, we never have to look at F. Yeah, Youngchul?
So the Meld algorithm is running against the local copy of this.
Yes, that's going. The Meld algorithm is running against the local cached copy of the last committed state.
How does the local copy track the version number?
How does the local copy track the version?
You said there's nowhere that version number is actually stored.
Well, as they're offsets. I mean, as it traverses down the tree and it grabs these, I mean, there's all. I mean, I'm cutting corners. You're right. I mean, there's information in here to figure it out. I mean, if you want to know, the way it works is, first of all, it turns. I don't know how much to say here. In order to, we try to be clever. All right. One way we're clever is we actually, for this dependency information on the left branch of D, we actually store it on D, so we don't even have to traverse the pointer. Right? It saves us, because these hops through the log are not cheap.
Yeah.
So we actually attach it to the pointer on the outgoing side. And if it looks like we have to traverse it, we traverse it, we follow it through. Okay. Now, we want to keep the pointer small, but the database is large. So we actually do indirection, because there's often many pointers within an intention record to different nodes in the same target tree. So we only have to store the real pointer once, and the rest are indirect through the structure so that we can compress the pointers quite a lot. This is partly how we get it down to 30 bytes. So maybe I'll just stop there. I mean, you sort of get the point. There's a bunch of clever systems programming in here that you have to do to make it work.
But the key idea is you got one absolute version number, and all you're doing is sort of adding.
Yes, there's one
right.
There's one absolute version number. That's right. Yeah.
Can you explain again what the depends on bit represents?
The depends on basically means, did the transaction read that earlier version, and does it know what?
Oh, okay. So if all the depends on bits are set to no, then it should know that the transaction is okay.
Well, no, because it could be that you modified. Maybe what happened is you modified F, and it's different than.
Okay, so this represents reads as opposed to writes. Okay.
Yeah, the dependency, and I'm cutting corners on the definition of the source structure version, and I'm cutting corners on the definition of depends on, because I'm just trying to get the idea across. But But you're right. I mean, you're thinking clearly about it. I mean, you're asking good questions that sort of are uncovering some of the muddiness in my definitions, which are for pedagogical reasons.
I sort of see what I was understanding. It's sort
Yeah.
of like it's I read this value earlier or something.
Yeah.
Or well.
It's for some reason this. I mean, could be a key range. You might have read the key range. You didn't really read the value, but you read the range covered by that subtree, and you're about to insert something, and that would normally create a phantom if somebody were trying to do a scan of that range. Now, we got a problem. The good news is transaction 3 committed. The bad news is it doesn't represent the last committed state, because transaction 3's state, if you look at its root, does not include the results of transaction 2. So we can't just use transaction 3 as being the last committed state. We somehow have to create a new root that points to both of them. And that new root is another intention, which exists in main memory only, is deterministically produced on any server that runs Meld, and it's an intention called an ephemeral intention because it only exists in main memory, and it logically comes immediately after the transaction, the committed transaction that caused the ephemeral intention to be created. So let's see how that works. So we need a new root which includes, basically replaces D. I mean, I already told you earlier when we did the walkthrough what it has to do. It has to replace D and include the right subtree created by transaction 3 and the left subtree created by transaction 2, so that it picks up both. So it points to E subtree produced by T3 and the B subtree produced by T2. It's a new intention. Physically, it's a real intention. You put it in main memory. It's got a version number. The next attention in the log is going to come after that version number. But everyone who's running Meld is going to do this and create this intention with this version number, so there's no possible confusion. They're all going to agree that the next intention in the log is going to acknowledge this little hole.
Who is going to append that?
It's not going to be in the log. If you look, it's not going into physical storage. It's not going onto the log. It's only in main memory. It only exists in main memory.
But all the Meld processors are going to produce it every time they...
Yeah. And what I'm describing is entirely deterministic.
It doesn't matter that it's not in the log.
Yes, it doesn't matter that it's not in the log because they're all going to produce it. They're all going to produce it in exactly the same way, indistinguishable.
I understood like absolute version number is some sort of offset in the log.
Well, the one thing you want to be sure of is any later, so this is now the last committed state in main memory. So the one thing you want to be sure of is that any later transaction's intention that references this, if you ever have to checkpoint it, you better checkpoint all the ephemeral stuff it's referencing, otherwise it's not going to be a legitimate checkpoint. It's okay to store it in the log because the Meld process on every server can reproduce this state, so it's okay for a later intention to point to it, but not if that later point is supposed to be a firewall against redo, that you shouldn't have to look, there's some point in the log you shouldn't have to look any further back in order to come up with the state. Then it better be that there's no ephemeral nodes in that state, because these ephemeral nodes can only be discovered by doing a roll forward here.
One of the questions before we started the talk, or right at the beginning, was about starting up a new server and how to start from. As long as you have at least one running server, you can piggyback on what they're doing, right? You don't have.
Right. So the question is, in terms of booting up a server, the easy way to boot up a server is just to grab its last committed state and the last pointer to the last log record it processed. From somebody else's server. Yeah, that's the easy way to do it. But if a total failure and all there is the log, then you got to have a notion of checkpoint to pick up. Yeah.
So the checkpoint records might actually materialize the ephemeral things in something.
Oh yeah, yeah, and it's just like any kind of checkpointing. I mean, if you have ephemeral records that have been sitting around in memory for too long, at some point, that's not such a good thing. servers do fail, you don't want to have to redo too much. So you do want to checkpoint them. There's stuff in the paper about how to do all that. All right, we'll go down one more. I think this is the last algorithmic detail. I didn't know how far to push you on this. There's another version number. In addition to the source structure version that I talked about, there's something called the source content version. That's the version number of the node that first generated the payload in its predecessor.
What is a payload?
The content, it's the data value associated with the key. So you've got the key, every record has got a key, and then it's got a payload, which is the rest of the record.
What is the predecessor?
Well, so you see, here's the issue, remember, nodes get replaced simply because something in the subtree changed. So when an intention is looking at the source structure version of the last committed state, it may see, oh yeah, that node changed. But it turns out the only reason why it changed is because of stuff in the subtree that caused it to change. The content of the node is actually unchanged. And the way it can tell is that the source content version of that node is the same as the source content version of in the intention, that the content has not changed since the point at which it was first generated. They both, right? Okay. So then we have in order to avoid having to actually diff values, we have a bit altered, which is true if the payload is different from the payload of its predecessor. And then depends on, and that was true, if the intention depends on the node n's predecessor's content. So let's see if I can reproduce this without getting confused. So the source content version of node 14 is version 1. So that means the content hasn't changed between version 1 and version 14. Stuff in the subtree's changed, but the content hasn't changed. But this guy now altered it. So 14, the content of 14 is different from the content of 13, but nothing earlier. So the new content version of that node is itself. The new content version says, from now on, this is the content version of this node is this one. Up until this point, the new content version of all these nodes was the same, because they all went back to V1. So now version 15 gets generated in some intention, and if its source content version is also pointing to V1, and its depends on is true, and if V14 actually committed, then we have a conflict.
So it depends on true if someone reads and then
Reads and then alters.
So it's always true except when we change a node just because we have to change
Blind
the
write.
nodes.
There are a lot of blind writes that go on. You don't really care what it was. You're just overwriting somebody's phone number. You're not incrementing it by one.
Well, no, but if I'm in an intermediate node, so if I'm going to modify an intermediate node, just because I have a new version that I don't depends on is not
And
true.
it's also false.
It's false.
Sorry?
It's also false in that case, right?
Yeah.
Blind writes is one reason why it would be false. The other reason is if it's just changes as a...
Yeah, so if it just changes because something in the subtree changed, or if it's a blind write, then depends on would be no. Okay, you get the point. So this is not the end of the line, but I'm just trying to give you a feeling for the level of complexity that there's a lot of this metadata, and you start thinking about all the different ways in which you can avoid traversing too deep and making sure your conflict test has no false positives, that you're not. You can sometimes cut corners by being conservative and well, we're not sure whether there's a conflict, but we also don't want to work very hard to figure it out, so we'll just declare it a conflict in this case. So we'll abort, even though maybe we didn't have to if we were willing to work harder. So it's this combination of precision and performance. Okay. So phantoms, I think I got carried away. So you can imagine, you don't need to read this. The concept is basically it's another one of these dependency information where you're now depending on a range, and so you have to keep there's a little bit of extra metadata of depending on an entire tree rather than just depending on an individual node. And you can even go further than that and include a key range if you want, because the boundaries in the tree may not be convenient relative to the key range that you actually cared about. You know, they may cover you may either need too many key ranges, or you may need to get a key range that's too coarse-grained for what you care about. So, let me just. So garbage collection. So one of the interesting things about these, talk about ephemeral intentions. Most of the time they don't last long, because most of the ephemeral intentions are high up on the tree, and once you generate them, pretty much every you don't get serial intentions very often, is what it comes down to. You know, most transactions are running concurrently, and there are some committed transactions that happened while they were running, and therefore they are going to have to generate an ephemeral intention to merge their updates with the updates of any committed transaction that happened in their conflict zone. So these ephemeral records are just going to be naturally replaced almost every time near the top of the tree. They last for like one transaction execution, and they're immediately replaced by another ephemeral intention. It's only, you know, deep down in the tree where they might end up hanging around for a while. So you want to be able to garbage collect them. So we can track them using an ephemeral flag or a count on each node that has ephemeral and descendants, so that we can easily figure out. So if you want to garbage collect them, you want to be able, you don't want to have to traverse the whole database. You want to just traverse down far enough to pick up all the ephemeral ones. And so by keeping track of which ones have ephemeral descendants and how many, you can limit the amount of traversal to just pick up. You only have to search down far enough to pick up the ones that are there. Or if it's really small enough, you could even just keep them linked in a separate list. We actually don't do that, but and then periodically you can run what we call a flush transaction, which is an identity transaction that just creates a persistent copy of all the ephemeral nodes. And it only has to do that for the ephemeral nodes that have been sitting there for a while unchanged. So, and it can tell by, it picks a threshold version number, you know, and just writes out all of them. It's going to necessarily have to write out all their ancestors anyway, but that's not going to help because they're all going to get rewritten quickly too. But the descendants will get made persistent and probably will not be rewritten. Oh, I guess I should have added here. Because it's an identity transaction, there's no conflicts. It can't conflict with anything. So this transaction is guaranteed to commit.
I'm actually confused about one point, which is what each server really holds in memory. Like I see the structure of the log that's kind of sitting on disk, but then it seems like each server also kind of is replaying the log, so it kind of has some chunk of that log, because it seems to use just that log information with the ephemerals in it to figure out the current structure of the database. But eventually it would run out of memory, right? I mean, it can't have the whole log, so it has to, it can definitely, so it's kind of like it has the log, but it can drop everything that it's not currently updating.
Just the current state, right?
It's a cached copy of the last committed state. Actually, it's just the portions that were recently melded or recently accessed by transactions on that server.
And everything else can be dropped.
Yeah, everything else can be
But
replaced.
the shape of what remains is kind of similar shape log.
I'm sorry. The shape of what remains.
I mean, the information, because it seems like what the server keeps track of is going to be kind of the shape of the tree, but it has to have all the metadata and all those potential transactions. Except it has kind of a subset of.
Yeah, each server will have, there's a certain overlap. Each server will have roughly the same, there'll be a large intersection of the cache that's the same on all servers because they'll all have accessed enough data to perform the meld on the tail of the log.
That's right. So each of them, and that cache really takes the form of the tail of the log.
And that's effectively the tail of the committed tail of the log will be in memory. Plus, they're each running transactions. Now, presumably, a large fraction of transactions are read-only. Even in a transaction-based system that's heavy on updates, a large fraction are read-only. Those transactions are going to be presumably different on each node, and so the data that's been cached for them will be quite different from server to server.
That's right, but my point is
But-
that so there's no separate data structure that represents the database in a different form than.
There's no other form of the database other than the last committed state in each of these servers.
That's right.
You know,
So the server
or
has kind of the tail of the log with its own transactions. And
Right.
the melds.
Right. So, or you could write a periodically you could write a checkpoint record, which is a lot like the flush transaction that's flushing ephemeral nodes. They're very similar, which identifies saying this is a committed transaction. The state that's accessed from here is indeed committed, and in order to reconstruct the last committed state, you only have to start melding from this point earlier in the log and just roll forward from there, and you'll be fine.
Is there some, so when you, how do you evict things from this cache? Is there anything smart you're supposed to do there, or can you really just do whatever you want locally?
Well, as far as the algorithm is concerned, the meld algorithm is insensitive to the cache eviction strategy, but no doubt performance will be.
Besides the obvious things of making sure that whatever you're operating off is there anything because of the way the algorithm works where it's like, oh, yeah, you want to make sure you don't.
Okay, so the question is whether there's anything about the algorithm's behavior that would influence the cache eviction strategy. I don't think so, because the main thing is that the algorithm is doing frequent updates to certain parts of the tree, and any rational, I don't know, maybe FIFO or something, there are cache replacement strategies that might actually evict data that has recently been updated, but that would be a bad strategy for this algorithm.
Common strategy.
Anything that's LRU-ish is going to be fine. So there's a bunch of other important details. Especially in a binary tree, but it can even happen in a B tree, the shape of the tree can change based on rebalancing or merges and splits. And so it's, I've been talking about sort of following paths down the intention and comparing it to following the same path down the database tree, but they may not align. Things may move between subtrees. And if they do, then the recursion is more complicated, because from here on down, the stuff that's in the left subtree is actually, some of it's in the left subtree and some of it's in the right subtree of the database, because there was some rotations that happened in order to rebalance. And so now you've got to get the recursion right. That was a couple weeks of my time. Deletions are always an issue in these systems, and especially because you've got to do accurate conflict detection. So you have the typical ways you include tombstones, and then you have to include version numbers for the tombstones. The tombstone says there was a record here, but it's dead, and here's all the metadata you need to know about it. And now the question is, well, how long do you have to keep the tombstone around? Because you don't want to keep it forever. Garbage collection. So the way we do that is every node keeps track for the 2 child pointers of every node. We keep track of the oldest version number in that subtree. So if you want to recycle the log, you pick some version number, and you just basically go traveling down the tree, and you start copying stuff from early in the tree, and you throw it into the end of the tree. And you can find it because it's just basically a traversal that says, if you can find the oldest node that's referenced in the tree, right? Then you can find the second oldest node that's referenced in the tree. And you just basically keep copying them over, And then when you've got everything before a certain amount, a certain space in the tree that's gone, it's not referenced, by looking at those back references on the root, you now know you can recycle the entire log from there on back, which means the log can wrap and it can start reusing that stuff. All right, this is a very, very simple algorithm. And then checkpointing, which I've mentioned a few times. What about performance? So I'm going to show you some graphs. These are our throughput numbers. There's latency numbers also. We count committed and aborted transactions as part of throughput because we have to process them all. And so it really doesn't, in terms of the speed of the MELD algorithm, it doesn't really matter whether they committed or aborted. That's really a function of what the conflict behavior is, what the access distribution. So the experiment I'll describe, it's a small database all in main memory, 128,000 keys. Keys and payloads are 8 bytes, so it's not a lot of data. We take serializable isolation, so the intentions have to include read sets. This is kind of a worst case for us because it means you have to store lots more information in the intention record. You've got to store all the stuff that was read, not just written. One of the things we learned very early in this is that just simply deserializing these intention records into a reasonable data structure in main memory is half of the processing time of MELD. And so you want to do that on a separate core, separate hardware thread. That's the first step in parallelizing this thing. Transaction size is going to affect MELD throughput. This is something, the question is by how much. And so does conflict zone size, which we call concurrency degree, because the more transactions between the snapshot you read and where you wrote, the more processing you're going to have to do to figure out the conflict. As the transaction size or the concurrency degree increase, you're going to get more concurrent updates with keys of common ancestors, even if there's no conflict. And that's going to force you to drill deeper in the tree to do accurate conflict detection. So even if there's no conflict, just the very fact that other parts of the tree higher up have changed is going to hurt you in terms of MELD performance. What about throughput? So the x-axis is the number of operations per transaction, and each graph is for a given amount of concurrency in the system, which is measured by the number of transactions in the conflict zone. So degree 1 means there's only one transaction between the snapshot that you read and where the intention landed. Concurrency degree 4 means there's an average of 4 transactions in between, and so on. And of course, as you would expect, as there's more and more transactions in the conflict zone, MELD slows down. But it's still a pretty good number. For example, with concurrency degree 64 here and 4 operations per transaction, we're melding 200,000 transactions per second. That's a very good number. So this is comparable, faster even than what you see for main memory databases. But remember that we're running this is updates across all servers, so then the numbers doesn't. Yeah.
This is my big worry. So now if I buy 100 times more servers, this will not scale.
Absolutely. That's why it was so important to optimize the heck out of it. This has a scalability limit.
So 200K, that's it?
That's it.
Okay.
That's it. So it depends. Now, what does that depend on? Well, it depends on the speed of the servers, and how many, what the ratio of queries to updates are. Only update transactions get logged and have to be melded. Queries are running off a snapshot. They're not in the picture. And then, of course, then we can play the same games everybody else does. If we reach a limit, we can partition. But we have a separate log per partition. But
instead of the hardware code being the main player, it's now the software code are the main player because you can increase this number by using improvements in software.
Yeah. That's so the observation is the faster you can make this algorithm, the better you can scale. I think you might be able to squeeze another factor of 2 out of this, but the wins are going to, you're going to get it like 5% at a time. You can do a lot of work. I don't know what the absolute limit is, but this was not a summer project. All right. I don't know how to explain this. There's a lot of effort. We built it 3 times, optimized it a lot. People doing different implementations were comparing notes and reading each other's code. I mean, it was. If you read the paper, you'll see. I mean, there's just a lot of detailed thinking went into optimizing this. So, you might be able to make it faster, but I think there are limits. We're getting pretty close to them.
How many? Let's see. So how many parallel servers? And there's sort of a cap on the number of parallel servers that are useful against.
Well, yeah. I mean, this also depends on the speed of storage too. So the fastest main memory database numbers I see are like 50,000 transactions per second on a single server, but that's all update transactions. If you assume the usual, like maybe 10-to-1 ratio of queries to updates, so now you're talking 5,000 per server, so we can hit 200,000, so you're looking at 40 servers. So that's, that's why I say a few tens. And it's also, but that's not the only bottleneck. I mean, right now, the network is the bottleneck. I mean, this is the ultimate bottleneck, not today's bottleneck. This is more than satisfactory based on today's networking speeds.
Also, yeah. I think you mentioned running Melding parallel, and it seems like you could, because you're kind of traversing these trees. So eventually you could do checks on different subtrees in parallel as you have more processes.
So you could do speculative execution of meld. And then bookkeep it so that so under the assumption, so basically you can be running meld in parallel on several transactions in a row. It's sort of like pipelining instructions on a computer, and as long as at the very end you can tell that everything it depended on is unchanged, you do a few little pointer flips at the end and you're done. So one could potentially do that. We didn't. Yeah, so, right. So the question is, if you have a lot of reads for some reason, like heavy analysis, so people talk a lot about real-time business intelligence. And so you're getting updates at a fairly nice clip, and you're trying to make real-time decisions against the very latest data. That's, current data warehousing solutions can't do that. Streaming solutions, well, they're streaming. They're dropping data on the floor. It's not a database. So this actually can be used for real-time BI. It's, you can run against, the queries run against a snapshot, they run against the very latest state of the database, but you're processing transactions at a very high rate in parallel.
The delay that you can tolerate too, pretty naturally, right? You just let them lag behind in the meld algorithm a little bit, completely independently.
Right.
And now they're 5-minute delays, sometimes.
Right. Well, you don't really have to delay them very much when you just run them against the latest state. All right, let me just.
Like give them lower priority, pulling pages or something.
Yeah. So I just have a couple more graphs. I'm out of time. Let me just wrap up. So the number of nodes accessed, just to validate where I said the reason why more parallelism, more concurrency causes the transaction rate to slow down is because the meld algorithm has to access more nodes. Not necessarily conflicts, but it has to drill deeper. And this graph basically proves the point. It's just the inverse. It's the number of nodes that are accessed as a function of exactly the same thing, the number of operations per transaction and the concurrency degree. And it's the mirror image of the graph on the previous slide. Right? That's throughput. That's the number of nodes accessed. So that is the reason. We're quite confident. But then the next question is, we did all this optimization. Is it worth it? Maybe we should just brute force and just traverse the whole tree. How much different would it be? Well, the previous graph already shows that it makes a difference. That if you start accessing more nodes, throughput goes down. Here, what we did is we we went in and modified the code to factor out all the optimizations. So it just always, it was exactly the same code, but it always traversed down to the bottom of the tree. And depending on, this is for read writes, this is for read inserts at different concurrency degrees. And basically, we were getting between a 3x and a 5x improvement based on. So it's, it's nice. It's not 100x. But then again, a transaction only accesses what? 20. So you can get a sense of how much it could possibly improve. It's got to somehow be a linear function of the number of nodes in the intention record. So 3x, 5x is, we think it's pretty good. There's, I already said, there's lots of optimistic concurrency control papers, but none that get into this kind of detail that I know of. If you do find anything, I'd be really interested in reading it. I don't mean to slight anybody. I just haven't been able to find it. By contrast, there's a huge literature on conflict testing for locking, which is the competition for this algorithm. So the bar of demonstrating that we had something that really worked is pretty high. You're sort of competing against 35, 40 years of optimization, and people still write papers on how to optimize locking a little bit more. And then I said, so you mentioned, Dan mentioned Lisp and functional programming. And after we did this work, we found, we were talking about it to somebody and who knows the functional programming literature. And he said, oh, this sounds a lot like this paper. And he pointed us, it's called OZen Store. Zen is a open source identity management system. And it was published in the International Conference on Functional Programming, not something we look at every day. And it's basically the same algorithm. All right? With no optimization and database granularity concurrency control. So, it's, which makes sense. In a directory service, you don't really get that many updates. So, but it basically, if anything changed, then they abort. And they explain it completely differently. They got a very different point of view on it. But it's the same idea, because in functional programming, as you said, you always do updates by replacement of the structure. And so, they don't call it multi-version, but it's basically a multi-version tree with optimistic concurrency control. So, it's sort of, when I first saw the paper, it was like, huh? Oh no. Yeah, but yeah, well, it happens. So that's it. So there is some opportunities for future work. We could apply this to other tree structures. As I said, we've done it on B trees. I don't know that we'll ever report on it. I don't think we've learned enough yet to really feel like there's a paper's worth of stuff to write, but I don't know, maybe. Using different storage devices for the log, maybe even for last committed state, I don't know. One could compare it with locking and other optimistic methods on multi-version trees. We haven't really, we just tried to make it as fast as possible. We didn't really try to do apples-to-apples comparisons with other algorithms on the same workload. And we're logging after images here. This is not areas. We're not logging operations, physiological operations. And given that the log is the database, that makes sense, because when you search back through this tree, you want to actually get the data. You don't want to get some operation. It's like, well, if you run this operation, you can find out what the data would be. That's probably not what you want. So, but maybe there's something that can be done with physiological logging is much more compressed than after-image logging. It has some other nice properties. Maybe there's something that can be done there. I just haven't really dug into it. That's it.
Like a lazy DB.
Lazy DB?
Yeah, sort of like
How so?
lazily evaluated.
Oh, lazy evaluate the database with physiological logging. Yeah, maybe.
So you mentioned you were talking about latency in the paper, so maybe I should just read that. But it's like there's sort of a difference in how you're paying for the cost here, right? Like if I touch, and you have some of those graphs, if I touch a lot of different nodes in a lot of different places in my transaction, I guess am I writing things down that I probably have to wait a little longer to see whether they're committed or not. Right, because I have to do a little bit more work to sort of sort through that. While if I take a lock, I might have to wait for the lock. But if I get the lock, I know that I just have to do my work, and then I'm done.
So I think the observation is optimistic is inherently, optimistic concurrency control inherently has more transaction latency because you do conflict detection at the end.
Okay, that's true.
You're not, you know. Although even there, it kind of depends on how you bookkeep it. And you could imagine, we already, Magda asked the question earlier, I mean, you can have a sort of a running summary of the updates that have happened recently so that you can detect. No, there's a metaphor here relative to broadcast networks. So if you've studied networking, you may have looked at something called the Aloha network, it's 1960-something, which was a radio broadcast network, right? So they broadcast, you know, off of this tower in Hawaii to, you know, and everybody's listening. But if everybody's broadcasting randomly and any two messages are broadcast at the same time, they're going to conflict, and both messages are lost. All right. So this sort of has that flavor, except one of them, in our case, and the nice thing about optimistic concurrency control is somebody always gets through. The first one always gets through. It's always the later guy that gets aborted. So, and to a first approximation, under most broadcast scenarios, if you only account for pairwise conflicts, you've got like some high 90% of them, 95% of the conflicts are going to be. You know, you don't have to look at three-way conflicts or four-way conflicts. Pairwise pretty much gives it to you. So if pairwise conflicts account for all of it, then basically you should get double the throughput of AlohaNet with the same conflict probability as whatever you calculate. So if you go back and read Kleinrock's analysis of this, you know, there's some classic queuing theory analysis of this under the usual unrealistic assumptions of Poisson arrivals and exponential service times, throughput is 17%. So you would expect the throughput on this to be something like 34% worst case. And I don't think you'll ever realize anything that low, but that's sort of another way to analyze it. You can analyze latency. I mean, I think a lot of the network analysis stuff that was done on broadcast networks can probably be reused here. No? No, thanks for sticking around. Thank you.